Good morning to one and all present in the class. I welcome all of you to the class of chemistry where we have the date 26th January 2021. In the last period, my dear students, we have studied about the classification of the organic compounds. So at last we have studied about the cyclic compounds, whether they are benzenoid or non-benzenoid. So here the question arises that how do we determine whether the given compound is benzenoid or non-benzenoid or whether it is aromatic or not. So to understand that we can have few things. So let us read the question. Let me read the question for you. How do we determine if the given compound is aromatic benzenoid or not? Here we have the answer, my dear students, that to determine if the given compound is aromatic or not, the compound must possess the following properties or following characteristics. The first characteristic is this, that the compound must possess planarity. What is the meaning of planarity? All the atoms present in the compound must be in the same plane. So all the atoms present in the compound must be in the same plane. That is how we can understand by looking at some example. Let's understand this with some example. I hope, my dear students, you are able to see what I am been writing. Are you able to see? I'm trying to draw something.
Yes, sir.
Okay. So now think this
Yes,
is
sir.
a benzene. Now, if you have this kind of benzene, we have this carbon available with us, my dear students. In benzene, we have six carbon. So this is what you can see here. So in benzene, we have six carbon. We are well aware that in benzene, my dear student, all the carbons, in benzene, all the carbons are sp2 hybridized. All the carbons, all the carbons are sp2 hybridized. So, when the carbon undergo sp2 hybridization, 1s and 2p. See, this is 1s and 2p orbital undergo, and thus a carbon will have three sp2 hybrid orbitals. These are the sp2 hybrid orbitals which are present in the same plane. And above and under this plane, my dear students, they'll have the orbital which do not take part into it. So this is how we represent it. This orbital which do not take part into the hybridization is lying above and under this plane. The same thing we can represent here in case of benzene, my dear student, that you can see that this benzene is going to have three orbital. See, this carbon is going to have three orbital, one, two, and the third one. Same way we can have this carbon having three orbital, one, this is two, and this is three. Same way if you look into this carbon, we will have three orbital in the same plane. You can see that all these orbitals are present in the same plane, my dear student.
Yes, sir.
Hello? Yes?
Yes, sir.
Hello, child?
Yes, sir.
हाँ बोलिए. So this is how you can see that this carbon have the overlap. This overlap, my dear student, we can show this way. See, this is the overlap here. Here, this is the overlap. Even we have the overlapping over here. Then we have the overlap. So this carbon and carbon, they are bonded with each other with this particular overlap. Now, my dear student, we can move and understand the overlap with the hydrogen. Each carbon is bonded with the another hydrogen. So this is how we represent this hydrogen, dear students. These all 6 carbon are bonded with 6 hydrogens in this manner, and again they have this overlapping. You know, these are the sigma bonds, so they have the axial overlap, and due to this axial overlap we can easily understand the sigma bonds formed. You can see that. So this is how, my dear students, all the sigma bonds are possible. Let me show you all the sigma bonds. This is sigma 1, 2, 3, 4, 5, and 6. Then we have the 6, 1, 2, 3, 4, 5, and 6 sigma bond here. Now you are well aware, my dear students, that above and under this plane, we have a particular kind of uh, orbital which do not take part into it. That is what we are trying to show. So above and under this plane, we have a p orbital available which do not take part into hybridization. So we can show this in this manner. You can see that for each carbon there is a pi orbital available. Now you can see that we have this pi orbital available above and under the plane. This pi orbital, my dear students, is responsible, sorry, this p orbital, I'm sorry, this p orbital is responsible for making the pi bond. So here you can see that there is a pi bond between these 2 carbons. Same way we can have a pi bond here between these 2 carbons. It is very easy to understand this pi bond. So here even we have a pi bond present with us, and then, my dear students, even we have the pi bond present over here. So dear students, you can see that there are 3 pi bonds present into benzene. So my dear students, it's easy for us to note down about these pi bonds. You can see this is pi bond, this is pi bond, and this is even pi bond. So if we really look into the uh, structure of benzene, my dear students, what we realize is that this carbon and hydrogen which are present over here in the benzene, this carbon and all the 6 hydrogen which are bonded, they are present in the same plane. So we can say our benzene is planar because all the atoms are present in the same plane. But my dear students, it is also noted that above this plane there is a pi electron. Under this plane there is a pi electron. You can see that there is a pi electron cloud above this plane, and there is a pi electron cloud under this plane. It's easy for you to see, my dear students, that there is a pi electron cloud above and under this plane. Here we have carbon hydrogen bond, and this is how. So this is what it represents, the uh, pi electron cloud. This is pi electron cloud above and under these planes. But you can see that all the carbon and hydrogen are in the same plane. So now, my dear students, what I really wanted to understand was the planarity. So you can see here, my dear students, that the first requirement for us is the requirement of the planarity. All the atoms present in the compound must be in the same plane. So this is how, my dear student, we realize that in benzene, all the 6 carbon and hydrogen in benzene, we have just seen that in benzene, all the 6 carbon and 6 hydrogen are in the same plane. Now, if you could not understand about the planarity, you can ask me the question. Is there any doubt that you cannot understand about planarity? Expecting a reply, my dear students.
No, sir, no doubt.
Good. See, once again, you see that all this carbon and hydrogen, all this carbon and this hydrogen, my dear student, all this carbon and hydrogen, they are present in the same plane, and that is why, you know, all the compounds who are aromatic or who have the aromatic character, they must be in the same plane. Then second one is complete delocalization of pi electron in the ring. So you can see that, my dear student, that in the benzene ring, the electron, this is the pi electron cloud, this is the pi electron cloud, and this is even the pi electron cloud. This pi electron cloud remains above and under the plane of carbon and hydrogen, and these pi electrons are completely delocalized. Completely delocalized. Now, how do we explain this delocalization? Let me try to explain you, my dear students, that how do we explain this delocalization. So, my dear students, if we have this plane of carbons with us and we have the various carbons present here, 1, 2, 3, 4, 5 and 6. We may have the another structure even, my dear students, and we have the various carbons present over here. We are well aware that there is a pi orbital available above and under the plane. Same way, this p orbital available above and under the plane. Now, sometime when the double bond is present in this manner, the same kind of structure can be even converted into this way, where we have the double bond or the position of double bond is changed. You can see that. It is very easy for you, my dear student, to understand that the position of double bond may change. You can see that this is how the double bond may exist. So once the double bond is present over here, in the next case, you may have the double bond, they have changed their position. You can easily understand by looking into this figure that this pi orbital, which is available above and under the plane, may have this double bond. So once the double bond is present between this carbon, my dear student, in the next structure you can see that there is no double bond present between this carbon. but now the position of the double bond has been changed. Same way you can see the double bond between these two carbon, which is not present over here. Same way if you look into these two carbon, there is a double bond present, but here in this two carbon, the double bond is not present. So if we represent the double bond here, in this case, the double bond is present in this manner. But if you look into the another structure, you will realize that the position of double bond has been changed. So my dear students, we are not able to locate where we are not able to locate pi electrons due to, this is what they are known as the resonance structures. So due to resonance, my dear students, we are not able to locate or relocate this pi electron or double bond, and that is why we can say that pi electrons are delocalized. To locate, let me explain the meaning of to locate. To locate is equal to, or the meaning of to locate is to determine the exact position. To determine the exact position. So when we say the electrons are here, they just move and go to the next position. When we say the electrons are here, they just go and move to the next position. When we say the electrons are here, they just go and move to the next position. When we say the electrons are here, they say that they just move and go to the next position. When we say the electrons are here, they just move to the next position. That means the pi electrons are delocalized. We cannot determine the exact position of the pi electron, and this is how we can say that in benzene, all the 6 pi, all the electrons are not present, or all the electrons cannot be localized. And then, my dear students, the third rule or the third requirement is known as the Huckel rule. According to the Huckel rule, there must be presence of 4n plus 2 pi electron. What is n? N is equal to the number of rings. N is equal to the number of rings. You can see that in benzene we have one ring, so we will write n is equal to 1, and therefore 4n plus 2 pi is equal to 4 into 1 plus 2 pi, that is 4 plus 2 pi, and that is 6 pi electron. So you can see, my dear students, that in benzene we have 6 pi electron. How do we get 6 pi electron? So we can say that we have 2 pi electron here, 2 pi electron here, and 2 pi electron here. Thus total 2 pi plus 2 pi plus 2 pi is equal to 6 pi electron. So in the benzene, your n is equal to 1. In benzene, n is equal to 1, and that is why 4n plus 2 pi electron gives us 6 pi electron, and thus benzene follow all these characteristics, and that is why we can say that our benzene is a benzenoid or an aromatic compound. And thus, my dear students, please remember that we can easily say that benzene is an aromatic compound. Benzene is an aromatic compound. How do we say this? How do we say that benzene is an aromatic compound? We can say this, we can say easily that benzene is an aromatic compound because, my dear student, benzene has planarity, all the atoms present in the same plane. Benzene has complete delocalization of its pi electron, and benzene follow the rule of Huckel rule, which is having 4n plus 2 pi electron, benzene has got 6 pi electron, and that is how we can say that benzene is an aromatic compound. So now if you have any doubt, you can ask, my dear students. Dear students, if you have any doubt, you can ask. बच्चों कुछ पूछना चाहेंगे? If you want to ask something, you can ask. Okay, my dear students. So if you do not have any question, we can move forward and understand about some of the benzenoid aromatic compounds. So let us look into the examples of benzenoid or aromatic compound. First example is, my dear students, can you see the screen?
Yes, sir.
So can you read what I have written? I have just underlined it. What have I just
Benzene.
underlined? Very good. So the first example is our benzene that we represent in this manner. This is our benzene. Now please understand, my dear students, that in case of benzene, now we just represent the bond line notation. Please understand that in case of benzene, we have just written the bond line notation. Then the second one we have is known as aniline. So aniline is having NH2 group which is bonded to benzene. This is aniline. Then the third example, my dear student, is naphthalene. This naphthalene has got two benzene rings. Now, see, all the atoms in naphthalene are present in the same plane. Even these electrons are delocalized, and according to the Huckel's rule, for n plus 2 pi electrons, whether it follows or not. So you can see that there are two rings, so n is equal to 2, my dear student, and thus 4 into 2 plus 2 pi electron, that is your 8 plus 2 pi electron, and that is equal to 10 pi electron. You can see that in each bond there are 2 pi electron. So my dear students, this is 2 pi, this is 2 pi, this is 2 pi, this is 2 pi, and this is 2 pi. Total 10 pi electrons are present in naphthalene, and this is how we can say that naphthalene is following the Huckel rule and it is an aromatic compound. Then, my dear students, we have one more example, or we can see, or we can look into some more examples, my dear students. Suppose you have the next compound which is known as anthracene. Let me tell you about the anthracene, my dear student. This compound is known as anthracene. The fourth example is anthracene. In anthracene, my dear student, we have, you can see that total how many double bond? 1, 2, 3, 4, 5, 6, 7. 7 double bond. So 7 multiplied by 2, that is 14 pi electrons are available. Here you can see that your n is equal to 3. We have 3 rings. So 4n plus 2 pi, that gives 4 into 3 plus 2, my dear student, that is pi electron, that is 4 3 are 12 plus 2 pi electron, and that gives us the 14 pi electron, and that is how we can say that this anthracene is an aromatic compound. Then, my dear students, we have the next one, which is a fifth example, and this fifth example is known as the phenanthrene. Phenanthrene. Let us look at the structure of phenanthrene. This phenanthrene has also got three rings, my dear students, and this phenanthrene is having these three rings in this manner. So phenanthrene has also got the pi bonds, and these pi bonds are available into the three rings in this manner. Again, if you look into the phenanthrene, we can see that there are 1, 2, 3, 4, 5, 6, and 7 multiplied by 2, that is 14 pi electron into the phenanthrene even. So as phenanthrene has got 14 pi electron, n is equal to even 3. So 4n plus 2 pi, that is also equal to 14 pi electron, and we can say the phenanthrene is uh, an aromatic compound. Apart from that, my dear students, we can even have some other compounds which are ions. So we will have the sixth example. This sixth example is the example of an anion. This anion is known as the cyclopentadienyl. This anion has got negative charge, and due to negative charge it has got 2 electrons available. So you can see that here, my dear students, here n is equal to 1, so we have one ring. This is pi electron present. So here we have 2 pi electron for this. This is even 2 pi electron, and this electron are also pi electrons, which are 2. So total we have 6 pi electron present in 6 pi electron present. The name of this compound is cyclopentadienyl. Cyclopentadienyl anion. So it is cyclopentadienyl anion, and this anion has also got 6 pi electron where n is equal to 1, and this is how it also follow the Huckel rule, my dear students. Then we have the next example. The next example is known as the cyclohepta trinyl cation. We have trin cyclohepta trinyl cation. So if you look into this cyclohepta trinyl cation, this cyclohepta trinyl cation has got 7 carbon, but it has 3 alternate double bond. And there is a positive charge available on this carbon. So again it has got 6 pi electron, and there is only one ring, n is equal to 1. And thus this cyclopentatrinyl cation is also a very good example of the aromatic character. So these are the 7 various examples of this aromatic character, and they follow all the rules, my dear students, which are required for being an aromatic character. Now if you have any doubt, you can ask. Dear students, have you understood it?
Yes, sir.
Yes, sir.
Thank you. So now we'll study about the examples of. Can you read what I have written? Please read. Please read what I have written, my dear students. I am just trying to confirm whether you can see the screen or not. That is my main purpose. Will you please read it for me? Can you see the screen?
Yes, sir.
So what is written? Please read it for me.
Example of those compounds which are non.
Very good. So now we are going to study the examples of those compounds which are non-aromatic or non-benzenoid. So let me give you the first example. The first example is the example of tropolone. Tropolone is a compound which is having a single ring with the 7 carbon. This tropolone has also got alternate double bond which are 3 in number. But apart from that, it has also some pi electron which are bonded with the oxygen. So here it is the example of 8 pi electron, because you can see that 2 pi electron here, 2 pi electron here, 2 pi electron here, and this double bond also has got 2 pi electron, and thus it has got 8 pi electron. For n is equal to 1, we need 6 pi electron, but here it is 8 pi electron, and thus tropolone is non-aromatic. Then, my dear students, let us look at the second example. The second example that we want to study about is known as azulene. This azulene, my dear student, is having such structure. Just have a look to this. Now, when we look at azulene, we will understand that it has 2 pi electron here. This is also 2 pi electron, and this also 2 pi electron. So it has got 6 pi electron, and it should be aromatic. But remember, my dear student, that this CH2 is exactly not in the same plane with this. So, this CH2 is available in some other manner. Let me explain you how. Just 1 minute, dear student. Now you can see that there are 2 different planes, and in this plane we have various elements available in this manner. So you can see that these are the carbons, and you can see that this carbon is available over here. There is a double bond between this carbon and this carbon, and the 2 hydrogen which are present, they are not in the same plane as this benzene ring. So these all 6 carbon and these 2 planes are different planes. So here the characteristics which is known as planarity is not followed, my dear students. Please remember that the planarity is not followed in this particular case, and as the planarity is not followed in this case, my dear student, we can say that it is a non-aromatic or non-benzenoid compound. Then, my dear students, we have the last compound which I would like to share with you is,